Welcome to Decarbonize and my series on electricity transmission. Today I'm going to talk about a group of technologies that can simply and quickly improve our grid at a low cost. None of these technologies require developing new right-of-ways or getting the kinds of approvals from regional transmission organizations that can take years to get. They also don't fundamentally change what the grid looks like. They just allow us to get more out of the grid we have. Collectively, these solutions are called Grid Enhancement Technologies, or GET. And the US isn't deploying these technologies nearly as fast as the rest of the world. If you want to know why, stick around. First, let's talk a bit about what motivates improving the grid. The White House just hosted a 3-hour summit that you can watch on YouTube, link below, on modernizing the power grid. Because it's required to meet our climate goals, support reshoring manufacturing, and electrifying heating and transportation. America's electrical grid is as congested as our roads due to decades of insufficient investment. This leads to reduced reliability and increased costs and emissions. For example, in 2003, an overloaded transmission line dropped into the foliage in Ohio. Because of congestion and inadequate control systems, this led to a power outage across much of the Northeast and parts of Canada. There's a great video about that on the Practical Engineering channel, and the link is below. If you'd like to get a more technical view on how the grid works than I'm planning on doing here, I highly recommend this video. A more common occurrence is that there's power available from a low marginal cost provider, like a wind or solar farm, but the power can't get to where it's needed because of congestion. So expensive natural gas peakers are fired up and the renewable energy goes unused, which is called curtailment. This costed ratepayers about $21 billion just in 2022. There are 3 classes of GETs: dynamic line rating, or DLR, power flow controllers, or PFC, and topology optimization, which for some reason I don't hear called TO. Let's start with dynamic line rating. The more power you can run through a cable, the hotter it gets. As you might remember from high school physics, hot metals expand. So as the cable gets hotter, it gets longer, which leads to sagging. At some point, the cable might touch something like a tree and cause a short circuit and a fire. So every cable gets a static line rating, which is the maximum power you can run through it. If the cable is getting close to its rating, then operators need to redirect the power to other cables, which might cause them to exceed their rating, causing a cascading failure of the grid. And since grid operators are inherently conservative, they assume it's a hot, sunny day with no wind when calculating the static line rating. But on a cold, windy day, they could safely run more power through the cable than its rating. That's the idea behind dynamic line ratings. By placing sensors near the cable, they directly measure the environment and use that information to provide a line rating that is appropriate at that time, which often allows more power to flow through the cable. In extreme situations, the rating might reduce the amount of power allowed to flow, increasing grid reliability and reducing the chances of starting a fire. One of the big benefits of DLR is that it doesn't take long to install, with most of the effort updating processes and procedures to take advantage of the increase in capacity. Following a traffic metaphor, this is like setting a speed limit based on the weather. It's snowy or foggy or icy, then speed limits would be reduced. It's a pleasant day, speed limits are higher. Next, let's look at power flow controllers. The laws that an electrical engineer learns in their first year of college when solving circuit problems is all you need to know to model the grid. Power goes in where there are generators and it comes out where there are loads. And in between, it follows the path of least resistance. Actually, the path of least inductance, but you get the idea. Power flow controllers are like valves that give the grid operators a bit of control over where the power goes, allowing them to prevent overloading one cable by diverting some of the power to unused ones. PFCs take a bit longer to install than DLR, but by utility standards, it's still pretty fast, just a year or 2. They're like the meter on-ramps to freeways that traffic engineers can use to prevent a road from getting clogged with traffic. Finally, there's Topology Optimization, which is a purely software solution that looks at the power flow on the grid, taking into account the dynamic line ratings, and provides guidance to the operators on how to configure the grid using tools like power flow controllers to get the optimal flow. Since it's just software, it's relatively easy to deploy once you agree to do it. This is like Google Maps or Waze that provides the information on the ideal route based on the traffic at the moment, but has no control over what route you take. The report Grid Enhancing Technologies, a case study on ratepayer impact, did a detailed study on the impact of GETS in New York State. They showed the dynamic line ratings has a payback period of less than 2 years, and the power flow controllers have a payback period of less than 8 years. By comparison, traditional upgrades, which includes reconductoring and building a new substation, had a payback period of about 15 years. This is not an argument against traditional upgrades, since these resources last 50 years or longer, so a 15-year payback is still good value. This is especially true because there are environmental and social values not considered, like better grid resilience during extreme weather events and lower carbon emissions. But GETS aren't widely deployed in the US. With near instantaneous payback and little to no disruption to operations during installation, these technologies are a no-brainer. But at this point, they're still rarely installed in the US. This map of power flow control installations shows 185 megawatts of capacity in North America, which is the same as Australia with a much smaller grid, and dwarfed by Latin America and Europe. That's because the governance of our grid is so complicated and the incentives are misaligned with the goals of clean, affordable, and reliable electricity. Much of the grid in the US is operated by regional transmission authorities, or RTOs. These organizations are responsible for operating an electric transmission system that they don't own. So they can't just go and install a power flow controller, though they can point out that it would be useful if one was installed. The regulatory framework isn't any better. At the national level, there's the Federal Energy Regulatory Commission, or FERC, which says everyone should look at GETS, but doesn't do anything to require that. The RTOs, transmission owners, and utilities answer to multiple state agencies who aren't necessarily aligned. Utility profits are set by state regulators and typically allow for a fixed rate of return, meaning they are incentivized to spend lots of money to make money, not to be efficient. Imagine a wind farm in Wyoming that serves customers in Oregon. It's seen curtailment due to transmission congestion in Idaho. The owner of the wind farm might want some GETS installed to increase their revenue, but they can't do that. The utilities that want to buy the wind power might want to see GETS installed, but they can't. And the owner of the transmission line in the middle can't because their regulators won't allow them to pass on the costs to their customers, since most of the benefit goes to other entities. So they don't install the latest technology. This complexity doesn't just impact GETS, but all elements of transmission. There are reasons to be encouraged. The Bipartisan Infrastructure and Inflation Reduction Acts both provide money to help bring GETS to the grid. California just approved a $7.3 billion transmission plan that includes out-of-state transmission that benefits California, and that will be paid for by California ratepayers. And FERC's new rules, that I will discuss in future episodes, include mechanisms to have those that benefit from a project pay for it, regardless of state borders. To sum up, GETS are great. They're a fast and cost-effective tool to make our broken and inadequate transmission grid a little better. But our primary problem is governance, not technology. And we're seeing this in our response to GETS, to underdeploy them in spite of their amazing return on investment and success elsewhere. To return to the freeway model, our current grid is like driving across the country if the federal interstate freeways had never been built. Every time you crossed the state border, things changed. California would use kilometers per hour. Fonts and colors would change on road signs. Maybe Louisiana puts their signs in French. And there would be no rational plan for where the roads would be built. You might end up with no way to get to the next state. You might have two cities a few hundred miles apart with no road connecting them. There would only be 3 places to cross the Rockies on 2-lane roads. To get to Texas, you would need a 4-wheel drive with high ground clearance. Until we have a workable governance model for the grid, electricity will be more expensive, dirty, and less reliable than it needs to be. Thanks for watching to the end. As a reward, you get to hear me ask for likes and subscribes. According to YouTube, and they should know, only 16% of my viewers are subscribed. So if you all subscribed, that would be enough for me to get monetized, which I wouldn't mind. In the meantime, you can support the channel by buying me a coffee. And if you have any thoughts or questions, please feel free to add a comment. I read them all and respond to most of them. And you're clearly interested in the grid, so you can watch my whole series on that topic here.